Hi, welcome. This is Lisa Schwartz with Berkeley Lab. Today's training for Clean Energy Innovator Fellows is about integrated distribution system planning. Next slide. So following my brief opening remarks, I'll talk about integrated distribution system planning at a really high level, give you an overview. And then Julieta Geraldez with Electric Power Engineers will present on forecasting both loads and distributed resources. Then Cody Davis from Electric Power Engineers will talk about planning for distributed resources. Then Natalie Mims-Frick with Berkeley Lab will focus in on virtual power plants and how they can help meet distribution planning needs. We have Samir Sakar with ICF, and he'll talk about identifying grid needs and evaluating investment options. And then finally, Sean Murphy with Berkeley Lab will talk about the data metrics analyses that states can ask for with respect to distribution planning. We will have Q&A after each section, and you can enter your questions in the chat box at any time. We'll try to do most of them live. So presenters, if they're just minor questions, go ahead and answer them in the chat box. But save discussion questions for live chat. The slides are posted at the link that will be in the slides. So I'm going to put in the chat box the link so you can get them now. And we'll also post a recording at that same place soon. Next slide, please. We have a really great slate of trainers today. I'll let you read their qualifications in the slides, but suffice it to say, these are some of the best folks in the field. Next slide, please. All right, and one more. So after this training, next month on December 19th, we have a training by Andy Satchwell at Berkeley Lab and Nancy Ryan, former California Public Utility Commissioner, among many other hats she's worn. So it's going to be great training. The registration is available now. I'll also put that link in the chat box. So it's December 9th, 2 to 5 p.m. Eastern, and it will cover a whole host of topics with respect to transportation electrification loads and how to plan for them, including EV rate design. We also have additional trainings planned for next calendar year, one on building electrification, another on equity, and then a shorter session to tell you a little bit more about what national labs do and how to get our research and technical assistance. And again, all the trainings are from 2 to 5 p.m. Eastern. Next slide. All right, this is a place to get out your phones, please. Snap this QR code for a real handy link to register for our upcoming in-person trainings on integrated distribution system planning. So this curriculum is all new. If you went to the trainings last year by chance, it's going to be all new for you. So we are hosted by the National Organization of Regulatory Utility Commissioners, the National Organization of State Energy Officials, Berkeley Lab, and this is funded by the U.S. Department of Energy. I think you all as fellows have a budget for travel, but if you do need travel assistance, there are limited travel stipends available. So go ahead and register now, but reach out before making your travel arrangements. Depending on your organization, you can reach out to Jessica Diaz at NARUC or Camille Norton at NASIO. So we'll be talking about best practices across the US for planning distribution systems. Our real focus is on incorporating electrification and distributed resources into local grid planning. We'll talk about stakeholder-informed planning processes, all in the spirit of achieving state goals. We'll tackle the challenges that you're facing and talk about potential solutions. And we'll talk about questions that you can ask utilities to get the information you can need to engage better and make better decisions. New this year, we're going to have office hours with all the trainers. So it's great to be in person and to ask your questions and get your questions answered, and also hear other people's questions and what their solutions are. In addition, there's going to be a half-day state action planning workshop facilitated by RMI, and this is going to bring together all the learnings from the training to help you develop some plans for advancing distribution in your state. And we'll have interactive discussions and peer exchange to support implementation. So again, you can click the QR code, register now for either Charlotte next month, December 11th and 12th, Detroit, March 11th and 12th. Both those registrations are open now, And we will have another one in the West, possibly in Salt Lake City, possibly in Arizona, to be determined in April. And then there is a tour in Charlotte on December 13th for EPRI's Power Delivery and Utilization Lab. All right, next slide, please. Here are just some of the resources that we'll post online, and I'll talk about more of them today. All right, let's start with an overview of distribution system planning. Next slide. All right, so just so that we're on the same page, what is it? So we're talking about assessing the needed physical and operational changes to the local grid. And remember, utilities have always done this. Once they built their distribution systems, they had to keep it running. They had to make upgrades for new loads, for changes to loads. They had to keep it, the operations and maintenance going. So they've always done this. It's an annual planning process for spending. These days, it's really a standard practice to have a longer-term capital plan over a 10-year planning horizon. And those solutions have to be updated with new information and cost estimates every 1 to 3 years. Next slide, please. So we wanted to make this a little interactive, so we each, most of us have a poll. So we wanted to know, how many states do you think require regulated utilities to file any kind of distribution system plan with the commission? Doesn't have to be an integrated plan, just any kind of plan at all. All right, we're getting 60, so ooh, good participation levels. This is great. All right, I think we can call it, Miles. All right. These answers are interesting. So I would have thought, if I wasn't in this field, I would have said 50. But it turns out it's only about 20 states. And it's interesting to me too, because I've been doing integrated resource planning in the bulk power system side for decades. And, you know, it's like, show your work, tell us what your plan is, you know, not just what's coming in this rate case. But I want to see what's coming, you know, in the next rate cases, and what's, you know, what's going to be in the O&M bucket. So it was instructive. I would have been with you. I would have thought it was way more states, not yet. All right, thanks, Miles. Next slide, please. All right, so here I'm showing what those states are that do require utilities that are regulated to file some kind of plans. We have different colors. So the pink are sort of the more integrated type plans, either, you know, a distribution system plan or an integrated grid plan. Some states have just dedicated grid mod plans, and this is typically in legislation, as in the case, you know, for the two yellow states. Some states just have a plan that focuses on distributed energy resources, like Nevada and Washington. And some have more cohesive, like T&D plans for transmission and distribution, but it's not all inclusive. You know, it's just like certain kinds of investments. New Hampshire had requirements, rescinded them, and then put them back. So now, once again, they're requiring integrated distribution systems planning. So this is really a fast-changing environment. We do have a report we published with our partner NASIO last year on ways that state energy offices can engage in electric distribution planning. And this is in order to meet the state's goals. Next slide. All right, so that map showed different kinds of plans. I want to just explain it kind of quickly. So first, there are these sort of improvement plans, and this is typically tied with expedited cost recovery for certain kinds of distribution system improvements. So in Indiana, that includes transmission, includes distribution, and interestingly, it includes storage. And that's, you know, it's they're like 7 and 9 year plans. I think they've gone to slightly different time period. Pennsylvania has something similar for the distribution system. So the utilities can make use of this improvement charge to recover costs. And this is not just for capital expenses. This is for costs for repairing, improving, or replacing eligible distribution property. So this is, again, really tied to expedited cost recovery. Some states, like I mentioned, Nevada, as an example, are only homing in on planning for distributed energy resources. So they have a lot of common elements with more integrated and broader distribution planning, but not all of the elements. And so in this case in Nevada, the distributed energy resource plan is tied to the timing of when the utility is filing its bulk power system plan or its integrated system plan. So it includes elements like locational value of distributed resources, DER forecasting, which Julieta will talk about next, hosting capacity analysis, which Cody will talk about after that, and the infrastructure upgrades that are needed in order to host additional solar and storage and electrification. It also talks about the non-wires alternatives that Natalie will talk about a bit, and Cody. Next slide. So a couple more flavors that I mentioned. Some states require utilities to file a grid modernization plan, and sometimes that's all, like in Nevada and Virginia. And sometimes you also have to file other kinds of plans. So it's tied to cost recovery. Typically, it's a request for approval of expedited cost recovery for grid investments, grid modernization investments and programs. And then what U.S. Department of Energy and Berkeley Lab talk about a lot is how do we bring all this together into an integrated distribution system plan, which is really a systematic approach to satisfy customers, to satisfy grid edge needs, to satisfy state objectives. And it includes a grid mod strategy, and it includes distributed energy resource planning. And it may, and it's ideally, planning across relevant domains. So in Hawaii, for example, they're planning across the whole system, distribution, transmission, and generation. In Maine, there's a statute that requires, they're a restructured state, so they're not planning for generation, but it requires integrated planning across transmission and distribution. So those are just some examples. Next slide. All right, this is an important slide. I always show it. Here's an update. So the Edison Electric Institute, just for the regulated investor-owned utilities, every year they collect information from their members to determine what is the projected spend in capital investments. And they break it down by segment: generation, distribution, transmission, and so forth. And here's an important point. Distribution system investments account for the largest portion of capital expenditures. It's about a third, stayed about a third for quite a while. And that's in 2024, a projected $59.7 billion. And again, this is just for the investor-owned utilities in the US. This does not include the municipal utilities, the rural electric co-ops. Next slide. So what are the potential benefits from improving planning processes in the state? Well, first and foremost, better oversight over those very high utility expenditures. It's really important. Making transparent these utility plans for investments in a holistic way before they show up individually, one by one in a rate case. So you're not surprised 3 years from now in the next rate case, you didn't realize that this other investment needed to be made in order to get the functionality that the utility was talking about 3 years ago. These holistic plans are really important. I believe when there is meaningful engagement with stakeholders, and in the case of regulated utilities, regulators, outcomes are improved. Just like we've done for integrated resource planning for decades, we can consider uncertainties under a range of possible futures or scenarios. We can consider all solutions to try to get to that combination of least cost and least risk, including considering distributed resources. And we can enable consumers and third-party providers to bring their capital, leverage their capital, and propose grid solutions and participate in providing grid services, like with grid interactive efficient buildings. Next slide. All right, so I talked about what sort of distribution planning is as a whole upfront, but what do we mean by this integrated part? So it all flows from the state goals, objectives, and priorities, and those define the long-term, high-level outcomes for grid planning. Integrated distribution planning provides a decision framework to facilitate long-term grid investment strategies that address the state and local policy goals, objectives, priorities, customer needs, and evolution at the grid edge. So it's looking holistically at all of that. And ultimately, having a shared understanding among stakeholders of strategies to address all these things is really essential. We took a look at what the goals were for states that required or provided guidelines for distribution system planning. And they're the ones that we've stood by for decades: safety, reliability, affordability. But also there are some newer objectives for some states. It might be transportation electrification. It might be increasing local resources, renewable resources. It might be emissions reductions for greenhouse gases or other air pollutants. And also we see some related outcomes, like we want to better use our assets. Some assets are hardly used at all, under 100 hours a year. Maybe we can do this a better way. And also, since we are seeing increased penetration of solar and storage and managed charging, can we improve our integration and use of all of these distributed energy resources to help meet our grid needs? So another important point I want to make here is that the utility is always doing its distribution plan, but when it shares the plan and files that plan and gets stakeholder engagement, we have this transparency that is so important and really is the hallmark, has been the hallmark of integrated resource planning for decades. And I think it's very important. Next slide. All right, this is a really simple point on this slide. Everything should start with the planning goals, principles, and objectives, and that should determine what grid capabilities are needed. And in turn, that determines the functionality we want and the system requirements that we need. So it really flows that way. And I think the state's role is to set the long-term high-level outcomes for grid planning, and states, 20 states at least, have come up with steps that they think are really important to achieve these outcomes. Next slide. So we talked about stakeholder engagement briefly. It does, in my view, like I said, improve the quality of proceedings and outcomes. I think there's advantage for utilities. You can potentially develop these solutions with broad support. You can build trust among parties when there is information and there's a real earnest interest in sharing the plans and explaining why these are needed, the investments and the additional expenditures. It can go well. So before the plan is filed, the utility can include significant input through, for example, working groups, which many states have, or stakeholder meetings like Illinois had. Those are examples before the plan is filed. After the plan is filed, it's normal, right, for stakeholders to file comments on the plan, and the utility is going to consider those comments, and ideally they would address, here's why we adopted that recommendation, here's why we didn't, or we need to study it more, we'll consider it next time. It's also really important for the utility to provide periodic updates. Depending on the state, the utility might be filing these plans every 2 years, every 3 years, or every 5 years, which is a very long time between plans. Next slide, please. All right. I think really the only thing I want to convey on this slide is that there's sort of the bedrock stuff like asset planning in the blue at the bottom, and there's the reliability and resilience planning that is, mostly throughout this whole thing. And then there's grid modernization that's layering on top. So when we're modernizing the grid to get to some of these functions that we need to ensure reliability and resilience in the future and to meet our state and utility goals and objectives, that's layering on top of a whole bunch of other architecture, technologies, and systems. Next slide. All right. This slide is a little bit much, but I think that the real point here is it's very related to the last point. You've got core components at the bottom of the graph. These are your bedrock systems that you need: your GIS, your geographic information system, your outage management system, an advanced distribution management system that many, many utilities are installing. So these are the core components that you need to unlock or enable all of these applications that you want to support a reliant and resilient grid that is modern in the future. So applications could include things like smart meters and DERMS or DER management systems. So this is a core piece of understanding that's very important for the utilities decision-making and for the regulatory and other state agencies' consideration of what the utility is proposing. Utilities have to install some of these fundamental systems, but that's not enough and that's not all. They're going to be layering on top of that with applications over time because they're not going to do everything all at once, right? For cost reasons, for workforce issues, a whole host of issues, right? Next slide. Here's an example roadmap of just what I meant. So here is Xcel Energy in Minnesota. Here's their plan, their long-term plan over a 10-year period. And they're showing you, in the green, these are things that are in progress. In blue, these are potential future items. These are things they're thinking about. They're indicating now when they're filing the plan, here's what we're doing near term. Here's our plan. But these are the additional applications, systems, and technologies that we're rolling out in the future. So everyone can understand over a longer term period, over a 10-year period, what's happening. Next slide. So distribution planning is changing pretty fast. And the reason is resilience planning is really important, especially with the extreme weather we've been having. And so you're seeing a lot of new state requirements for utilities to file resilience plans, like frequently, all different flavors, whether it's wildfire plans or plans to, reduce storm outage costs. And bulk power system planning, integrated resource planning, there's a real interest in trying to coordinate distribution planning and bulk power system more closely. Local planning, your city, your local area may have its own plans, whether it's economic development or it's greenhouse gas emission reductions. There are these local plans that really are going to drive some decisions. And it's important for the utility to, their plan to really recognize that and make sure it's part of the mix. And then distributed energy resource costs continue to decline. Storage is something that customers are very interested in for resilience primarily, and also in some places to help reduce their cost in tandem with solar. So all these things are all these new inputs are kind of changing how distribution planning is happening. Next slide. All right, this is another time to get out your phones. If you click here, you'll get to our integrated distribution system planning website that has a lot of resources, but you'll also get specifically to this diagram. And this diagram is something that you can just push the buttons and play with. There is stuff under the hood for all of these buttons. And so you'll learn a lot more about what I'm talking about when I'm talking about an integrated distribution system planning framework. And we will be talking about this framework at the live training next month in Charlotte and again in Michigan and out west. So you can see the gray bar at the top, state and local policy goals and planning objectives, everything's flowing down from that. Next slide. All right, so we cover 17 topics. We could have covered a lot more. It's a lot. So for each of these topics, we really, we provide very succinct information. So I think it might be really helpful for you to gain a better understanding of what we're talking about. Next slide. Here's what we cover for each one of those 17 topics. First, what is it that we're talking about, right? What is hosting capacity analysis? What do we mean by when we say we're doing forecasting for distributed resources, for distribution systems? It's different. So what is it? What are we talking about? Why is it important? And what are, the common questions, frequently asked questions? What's my role? I work for, a utility, or I work for a state energy office, or I work for a tribe. What is my role here? I'm a consumer advocate. So, and what are the responsibilities? What are some of the best practices we're seeing in each of these areas? What are the current practices that states and utilities are doing right now? What's sort of typical practice? Then we have flow charts, things like inputs and outputs, so you can see like what information you need and what comes out the other end, and what are the methods, how are we turning the crank to get the outputs. We have a host of tools. We're a national lab. We have plenty. Our fellow labs have some, and we also list the proprietary tools that utilities are typically using, and some publicly available tools beyond lab tools. And finally, we have an annotated resource list so you can learn more about any subject you're interested in. Next slide. All right, another place to take out your phone, but there are links to all these on our website. So we in spring, we put up a catalog online of all of the state's distribution planning requirements in those roughly 20 jurisdictions. And we also have a data visualization. You can toggle switches, and you can, if you don't have distribution planning guidelines in your state, you can do a presentation using the material here to demonstrate what other states are doing. So you've got a baseline and some benchmarking you can do within your jurisdiction. We will, by January, have a forthcoming companion report. Next slide. That goes into a lot more detail than what the online catalog does. We also have a bunch more resources that will be published over the next few months, in the summer a little further. So I talked about how important data and metrics are. So we have two flavors of this. We have just for distribution planning, what are the data metrics and analyses that states can ask for? And Sean Murphy is going to talk a little bit about this report at the end of our webinar. So I think you'll be really interested in it. It's just brand new information we haven't even published yet. Miles Collins, who's on this webinar, he's leading a report on the same topic, but for resilience planning. Cost effectiveness evaluation for grid mod investments. This is such an important topic. Paul DiMartini and I and Jason Ball have a report that's under review right now. If you're listening and you have a copy, we hope you send us comments by November 20th, because we plan to publish really soon thereafter. Natalie Mims-Frick on the webinar, she is leading up a report on how do you deal with all the challenges for cost recovery for grid mod investments? Where is it going well? Where is it not going well, and why? And then finally, just like our interactive framework for planning for distribution systems, we're going to have a similar sort of interactive framework for grid codes. That is the whole operational aspect of distribution systems. Next slide. All right, we've got more resources in the slide deck. One more. We have a new round of in-depth technical assistance that we can provide to public utility commissions or state energy offices. The application process is open now. It'll close January 17th. So I encourage you you can just type in Berkeley Labs State Technical Assistance, and this will pop up. So if you're interested in more detailed, longer-term assistance, please go to that application process. But right now, if you need help, there's a help desk and there's an expert match where you can get more immediate assistance, a little bit shorter time period. Next slide. All right, I think that's it for me. I was going to maybe have 1 minute for questions, because I think a lot of the questions you have may be answered by other speakers. Miles, do we have any questions from folks?
At least I don't see any in the chat, but I'll
All right.
encourage everybody, if you'd like to ask, here's your time.
Well, I'm fine with going directly to Julieta Heraldez with Electric Power Engineers to tell us about forecasting loads and distributed resources. Julieta?
Great, thank you. I'll introduce myself real quick while the slides pull up. So I'm Julieta Giraldez. I'm Director of Integrated Planning at Electric Power Engineers. And I'm going to talk today about one of the key inputs of planning is what are we planning to? So for that, we're going to talk about load and DR forecasting. So if we go to the next slide, the agenda that I have for today is what has really changed in load forecasting for distribution planning. What is it used for primarily? So what's the use case that is used for in distribution planning? And then getting into the details of how we do it. So going from base load to now net load, so having to include the DER and demand side modifiers. And then we'll talk about some future considerations that were already touched on by Lisa, but the importance of looking at scenario planning and potentially in the future climate change and extreme weather impacts. If we go to the next slide, talking about what has changed. Next slide. So demand has been flat over the past 20 years, which means, or even decreasing in some areas. And so it means that really the load growth was driven by local load growth from new customer and businesses. And utilities, and especially in distribution planning, they had time to react to that growth within several years build an infrastructure or come up with a local plan responding to the local growth. And the past consumption, in terms of trending things out, the past consumption was a good representation of the future. If we go to the next slide, the issue now is that using typical load and weather is not necessarily sufficient anymore to forecast future load. One of the key changes is that customers are adopting new technologies behind the meter. And so now we have a new need to understand where and when those technologies are being adopted. And these are following rapid adoption trends. And so that's why it's important to be a little bit proactive. And then the last bullet there is that we're starting to understand that past weather is not necessarily representative of future weather. So that is sort of a consideration that we're starting to develop methods and ways to include it in the forecast. Next slide. The other great change and why, sort of those customer technologies are being adopted is that now the forecast is greatly influenced by policy. And so we need to understand and have some coordination from federal to state to local and utility policies and goals. Those are affecting and need to be considered in the load and DR forecasting exercise. But they are harder to quantify and also to predict. Is the policy going to change? And then those sort of policies need to be converted into quantifiable inputs assumptions for this technology adoption and impact into the grid. Next slide. So what is the distribution planning use case? So if we go to the next slide, before talking about distribution planning, I sort of wanted to bring up some background on load forecasting because it is currently being performed typically annually by multiple entities within a state or a region and by multiple departments within a utility. And so today we're going to be focusing on the distribution planning use case. And it's important to note that traditionally, distribution planning has performed their own local area forecasting. And it is not typically coordinated necessarily with the financial department's forecast or the ISO forecast. And those are typically used for resource and transmission planning. And so it is one of the aspects that it's starting to change is that now we also need coordination. Are we planning to the same thing? If we go to the next slide, load forecasting departments and ISOs typically forecast energy and coincident peak demand, so system level peak demand at a system level. So maybe it could be a service territory or an entire ISO or a state. But that has been really hard to apply to the local area. And so distribution planning has simply come up with their own non-coincident peak loads. So the distribution of the feeder might not peak at the same time as the system peak. And that is the need is typically at the substation or feeder level to determine if the infrastructure is big enough now and is it going to be big enough in the future. So we go to the next slide. The load and DR forecasting has been typically used in distribution planning for capacity planning. And that is to evaluate that non-coincident peak demand with respect, so the non-coincidence with respect to the system peak in this case, at the distribution substation or feeder head. And then if the forecast exceeds the rating in the 3 to 5 year time frame, I have there 5 to 10 years, but it has typically been sort of a short-term look in distribution. Then if it exceeds the rating of the asset, come up with a solution. It could be wires or it could be non-wires. If we go to the next slide, we're going to be talking now about how distribution planning utilities have typically come up, but also what is needed to come up with that load forecast. And we're going to be talking about the need of going sort of from base load to net load. So include not just what the load would have done, sort of the native load, but also new customer business growth, economic growth, and DRs. How all of those demand side modifiers are actually going to modify that base load to truly come up with a net peak load. If we go to the next slide. So here I have sort of how we would go from understanding the base load to the net load. So I think if we click, there are some maybe interactive bubbles that are going to appear. That's right. And so what has most commonly been done is, and it's important to understand what utilities are doing, is what is their starting point? How do they determine what the existing base load is? That typically comes from a SCADA measurement, so the measurement at the feeder head or at the substation. And then the local area planner might adjust that value based on economic growth and new known customer business in the area. So if you click on the next one, these are the most commonly applied. We're going to talk a little bit about those right now by distribution planning utilities. And it's typically the local area planner that is going to decide what information it has on known customer growth and what percentage he's going to apply on economic growth. Now that projection, what we're seeing, and it's important to also linking this back to what Lisa presented to sort of meet the state and objectives and goals, it also now needs to be adjusted by other demand side modifiers. And these are less commonly applied, but they're becoming quite crucial to understand, which are energy efficiency, solar and battery, but also EVs and building electrification, to truly understand what that net load is going to be. And as we can imagine, that net load now, it's important to try to understand if it's going to change over time. So the feeders or substations might be peaking at one time, but with DERs, they might change when they peak. And those types of aspects are very important to understand and to make sure that we're considering sort of what's coming when we plan the infrastructure. If we go to the next slide. So questions to ask when sort of reviewing that first bar that I had on the previous slide, which is that base load forecasting. So regarding phase load, it is important to understand how the distribution utilities are processing that SCADA data to determine the starting point of the existing load, that from there we're going to add load growth and other demand side modifiers. And if, for example, they're disaggregating solar, so solar might be already present in that measurement, are they backing it out or not? That's important to understand. And then the other aspect that it's important is whether that load is normalized based on historical weather patterns at all, or if it's simply they're just using the measured load on maybe the previous year, but there's no statistical analysis performed to understand on whether that year the weather might be unusually mild or unusually hot or unusually cold. And so a best practice is to sort of do that statistical analysis to come up with some weather normalization of the existing base load. And then it's also important to understand where the economic growth is coming from, so where that assumption is coming from. It is typically an annual percentage growth applied to a substation or a feeder to extrapolate that out. And if that is based on any trend analysis performed using demographics and local economic indicators, or it is a default or left to the local area planner to choose. So that's sort of important questions to ask. If we go to the next slide. I have here two slides on weather normalization. I'm going to skip in the interest of time because we have quite a bit of to cover. But I just wanted to provide a little bit more information on that sort of statistical analysis. And then the distribution utilities that do perform these sort of weather normalization to understand what is the normal load and not miss, for example, if the peak this year happened on a weekend that might have been lower, or whether it was an extreme. Try to normalize that for planning. And what they typically use when they apply the statistical normalization in distribution planning is they plan to the 90th percentile load or weather. So that would mean using a 1 in 10 extreme weather event or max or weather event to calculate that peak load. So I'm going to skip the next slide, 15, and we can go to this one, which is I had shown in the base load to net load diagram Also that utilities typically and local area planners use known new customer business requests. So this is businesses typically larger, so they don't do it for residential, but they do it for larger than certain kilowatt rating. They sort of keep track of this new planned load, and they might add it or not to the local forecast for that feeder or substation. And so it's important to understand, be transparent about where this data is coming from, understand how utilities are tracking these loads, and do they do any manipulation of likelihood of these loads actually materializing? So how can they be more or less sure, and are they doing any derating when they include this? But this is sort of becoming a big deal because they are increasing these sort of step loads and planned loads, and are driving a lot of the needs, short-term needs. And so it's sort of important to understand, could we have been able to predict them? And when we have the information, how it's being used. If we go to the next slide, we're going to talk now about the last element of modifying sort of the base load to net load, which is to include demand side modifiers and like DERs. So these are critical now to start including in distribution planning. I would say that it would be very interesting to do the same survey that Lisa did on states and distribution plans. It would be interesting to do a survey on how many utilities actually include DRs to date at the distribution level. My sense is that the majority don't include any DRs to date. And so some of the questions that can be thought together when sort of thinking about including them is, what is the spatial geospatial granularity needed? Typically for distribution planning, it's going to be substation or feeder level. What kinds of DRs are we going to include? The forecast horizon, how long are we going to go, and the temporal impacts of when these technologies are expected to show up and how they will behave. And then finally, what targets are we planning to? Which I think this really relates to what Lisa was talking about. So some of those common objectives and goals that the utilities need to plan for, these are things that can be set in those discussions. What are we planning for in terms of DERs, so that the state and the utilities are planning to, or see the same future, planning to the same thing. Typically, distribution utilities that do include DRs in their load forecast don't truly necessarily determine that forecast. So they're going to use a target from the a corporate forecasting department, or now a lot of them are using these state level targets. And what they're going to do is perform a disaggregation of where and when those technologies are going to see the impact on the distribution system. So if we go to the next slide, we're going to talk about some of these disaggregation techniques. So it's not necessarily coming up with a forecast, but if we agree that by 2030, by 2035, we expect, from the state is a certain amount of solar or DRs, how can we perform that disaggregation of how it looks on the distribution system? So these are some disaggregation techniques used today by distribution utilities. The first one is sort of the easier one to apply, which is the proportional allocation. And this means you allocate a DR technology based on existing load or number of customers or other variables. This is commonly referred to when you hear the peanut butter approach. This is sort of what it means, is a proportional allocation based on some variables. And the issue is that it might not capture very well the way technologies are actually being adopted, especially the where. And it might miss local DR growth pockets, which are extremely important now to be included in distribution planning. And the more advanced methods that are being used are propensity models or adoption models, because they do a better job at sort of capturing the customer behavior and the customer willingness to adopt. And so these models are based on a customer type, socioeconomics, other factors such as, is my neighbor adopting or not? And what is typically done is you rank customers or areas by the likelihood to adopt a given technology, and then you meet sort of that state target, or you calibrate to that sort of state goal. So I think this is what I have regarding DRs. If we go to the next slide, we are going to talk, well, key questions to ask regarding DRs. So where are we planning to the same thing? Where are these targets coming from that we're using on DRs? Are DRs explicitly forecasted? Are they modifying that peak load to bring it down or up based on the specific technology? Is 8760 modeling being done? And how is that sort of adjusting a future peak load or not? This is key because it really is one of the key aspects that we want to understand, that sort of load profile across the day and the seasons, and if solar or EVs are going to modify that time of when it peaks. And then what are the behavioral assumptions around DRs? And so this is becoming more and more important, less so with solar, that is a weather-driven behavior. But now we have a lot of DRs that for which the behavior, like EVs, or even, demand side management, what are we assuming in terms of when, where, and managed charging or not managed charging? All of those are very important things to now consider when we put together the forecast profiles of the DRs and the load to ultimately understand the potential future behavior of the load. If we go to the next slide, I think I have a few other sort of future considerations. If we go to the next slide, we're going to talk a little bit about scenario planning. So this is very important. Distribution planning, and this was mentioned already by Lisa, but distribution planning has typically used this as circled method of forecasting, which is a very deterministic single point into the future forecast. Now, it is apparent that with the policy changes, uncertainty of how fast or not, the amount of technologies, the behavior, we are really seeing the need to encourage moving to more the L2 alternate futures here, which is, we're still doing sort of deterministic forecasting, but we're considering multiple futures. So this could be different amounts of DRs, for example. It could be different behaviors. It could be different adoption pace, fast versus less fast, to understand really what is the bookend, right, of what the infrastructure might be having to meet, and what are some best solutions for that, and de-risking factors that we can be looking at when we talk about the solutioning, which other presenters are going to dive into that today. I was going to say one more thing, but I forgot. Scenarios. Oh, well, if it comes back, I'll share it with you all. We go to the next slide. A little bit more about scenario planning and the factors, as I was saying, that are need to be considered. My thought came back. One of the important aspects why we want to do scenario planning is that a lot of these DRs have a very sort of an S-shaped or exponential adoption rate. And so we've been talking about this figuratively sort of as a hockey stick. And so if you don't look at potential scenarios, what you might miss is sort of that hockey stick of adoption where you are suddenly fine, but you didn't see that then a lot of the infrastructure is at risk if we change a variable or an adoption rate or a speed slightly. And so it's important for that proactive planning to be able to consider those scenarios, to have more robust plans, also identify no regrets investments. If we go to the next slide. The last sort of aspects I was going to share, this is to start thinking about, but to tell you the truth, I haven't seen it applied to distribution a lot. But we were mentioning already that it is important to do sort of the weather normalization or understand what the normal load is based off different weather patterns. So that is one thing, but that those methods typically used historical a behavior to determine that a normalized load. What we're seeing now is, well, maybe those statistical models based on historical might not really capture those extreme weather events that we might see in the future. And then the models themselves, the econometric models that we might build of how load responds to weather, might not be trained on these extreme weather events. And so this is sort of an area of research of how to include these both for hot and cold weathers on the modeling itself, but also what data and climate weather models can be applied to better capture weather patterns that might not have been seen in the historical data. And if we go to the next slide, I think so questions to ask regarding these two more advanced aspects is, again, do utilities perform a single point forecast, or do we consider a range of scenarios and probabilistic methods to determine what the loading might be on the infrastructure? And then what weather data is used, and does it or not include effects of climate change? And this is important if we're really looking at long term. So if some of the utilities are looking, past 10 years, it is starting to be quite important. ISOs are really ramping up to do that, to include climate change effects on the load behavior. And so I think I have one more slide on sort of these best practices regarding load and DER. So definitely understand, is the utility directly using sort of last year's load to determine the starting point, or is there any sort of statistical methods being used to understand the history and normalize the load? Starting to understand, really what makes up that load by feeder and substation. So the customer counts, the customer types, the socioeconomics to applied load and DER growth, what adoption models are being used, and load shapes. Are we also being able to leverage maybe some of the AMI data to understand better the 8760 behavior in these feeders and substations? And then last but not least, what I already mentioned, but the idea of using multiple scenarios. So could we look at potential different futures that might happen to do a little bit more proactive and risk identification of over and under predicting? And I think I've made it to the end with 5 minutes for questions.
That's great. Thanks so much, Julieta.
Yep.
I know Julieta threw a lot at you. For folks who have questions, you can feel free to raise your hand and we'd be happy to call on you, and you can just say your question out loud, or you could put a question in the chat box. Anybody have any questions? All right, well, we're going to go to a related topic next, which is distributed energy resource planning. And so, Cody, if you, we can get started with you. Miles, you're going to bring up those slides.
Awesome. Thanks, Lisa, and great to be able to present to y'all today. Cody Davis, I'm a senior principal engineer for electric power engineers in the distribution and grid mod space. Here to talk about some topics related to DER planning, specifically hosting capacity and non-wires alternatives. So on the next slide, we'll start with that piece and move right on to the next slide from there. So an introduction, when we talk about DER planning, what is a DER? On the next slide, you will see the universe of DER systems. Everybody has a different kind of working definition depending on where you are. Generally, DER kind of encompasses all of the ways of reducing load or injecting power in different forms. So solar is obviously probably the most common. Wind turbines are in there, battery storage, CHP, in some definitions, energy efficiency, some grid interactive buildings, potential services are all kind of lumped in with this definition of DER. May vary by region, but these are all kind of relative to what we're talking about in some sense or another. On the next slide. So if that's a DER, what does it mean to do DER planning? Well, forecasting is a big part of that, which Julieta covered in a lot more detail. So I'll kind of skip over that one, but hosting capacity analysis is a part of planning. This is the capacity equivalent for power injections. Non-wires alternatives is sort of the DER as a resource to address some of the other like distribution challenges around reliability and capacity. I saw a question pop up in the chat for why isn't nuclear considered? It hasn't been commonly just because it's typically not interconnected at the distribution level. Most of DER is sort of the systems that interconnect in the like 4 to 34 kV range. It's possible to have a nuclear that does that, but just based on the scale, historically, it hasn't been as widespread with like small modular reactors or other kind of innovations. There's definitely potential. But anything that's a DER like connects to the distribution and either injects power or reduces power consumption, generally in kind of a coordinated fashion. So as I mentioned, we're going to dive into hosting capacity and non-wires alternatives today on the next slide and the next slide after that. So hosting capacity is an overview. This is the amount of DER, generally of a certain type, although not always, that can be interconnected to the system without basically making things worse, right? Without having to make system upgrades. So if I have 5 megawatts of hosting capacity, I can add 5 megawatts of generation before things start to break down. Generally, these analyses are kind of based on a subset of planning criteria that are kind of the same ones studied in DER interconnection for where do I need to make upgrades, right? So thermal limits are a big one. Over voltage comes into play if you have potential for voltage violations. Reverse power flow limits across equipment that cannot handle reverse power flow. So either into the transmission system without the right protection upgrades or like regulator controllers or similar, and then some protection considerations as well. Generally, hosting capacity is kind of shown in a map format, although it doesn't have to be. There are values in kind of providing some tabular information as well that can kind of both be used for different things. Generally, hosting capacity kind of as a rule is an analysis of the entire distribution system, and it's generally required to be refreshed on a pretty regular basis. Because of the scale of what we're dealing with, you may not get as accurate of a result as you would get from an interconnection study, just because in an interconnection kind of detailed study, you have an engineer doing all the individual model prep and validation for every individual model. That does happen for hosting capacity, but you're also dealing with a lot larger scale. So you may not get kind of quite the same level. There may be some automation going on that kind of glosses over some of the details that a human person would catch in that process. So it's generally good, but it is kind of a scale product, and that's worth keeping in mind. On the next slide. So hosting capacity has a couple different use cases. The development guide case is kind of the most common. This is like helping developers find good sites by making information about which sites have available capacity public. We also see hosting capacity used within the interconnection screening process, right? Which makes some intuitive sense. If you know about where you're starting to see constraints, that can kind of feed into the screening process and help make it easier to interconnect in areas with capacity. It's not always as simple as that, but that's kind of the idea. And then last, as a distribution planning tool, the first step in planning for DER growth is to know where your constraints are, and hosting capacity is sort of the input to that process. So all three of these see some use, and we'll dive into each one kind of in order. On the next slide. So facilitating efficient project siting. This is the most common use case. The kind of goal here is to empower developers to have information, but from the utility side, there's a benefit. It's not just a thing that you do because you get ordered to, or because it's beneficial to developers. If you do it right, you can help reduce the number of what I'm calling non-viable applications. Systems that come in that are unlikely to make it through the interconnection process due to cost. Maybe they're not in the right location. Maybe they're really far from the substation. Maybe there's 15 systems ahead of them. If you can keep those types of applications from having to be filed, you can reduce the amount of kind of effort that it takes to move through the queue process. So there is some value there too. Generally, these maps are kind of put together as sort of a heat map approach in visualization. In some cases, this is really useful, but it really depends on how geographically granular these are. You can see on the upper right here, these are zoomed pretty far in, so you get pretty good granularity. Other maps from other utilities may have much, much larger areas that make it harder to use effectively. The most effective information to have for this use case is basically every piece of information you would need to effectively site and size a project. This would be calculated hosting capacity, information about queued projects, load profiles, grid constraints, locational information, down to as granular as you can get it. All of that plays into having a good idea of the siting and sizing. On the next slide. Okay, so what kind of information is in a hosting capacity map that you'll see that's really useful? First, substation, locational, and like hosting capacity calculated data. This is like, what are the constraints? What kinds of equipment inside the substation may be impacting hosting capacity? For example, is there a load tap changer on the transformer? Is it rated for reverse power flow? Substation locations are also, how close are you to the substation? Generally, the closer you are, the higher the hosting capacity because the system is stronger, although not always. Feeder locational data, kind of the same thing, but we can see where all of the feeder components are, how much hosting capacity is available at different points on a given feeder, how likely system upgrade costs are to be incurred at those points, and then some other equipment information that may impact it. Voltage supervisory reclosing as one example on the protection side. Other information that's valuable is not just the resulting calculation, right? Oh, there's 4 megawatts of hosting capacity, but at which criteria were evaluated and at what level did they start to have violations? So if I see 4 megawatts of hosting capacity total, and that's because of an anti-islanding requirement, but the next lowest one from there is like 9 megawatts, then if I pay for that anti-islanding upgrade, I can get quite a bit of equipment size on there, right? If the next one up is a 0.5 megawatt, it may not make sense, or I may want to size accordingly. So knowing at what level some of these different constraints can be violated can help you pick the right system size when you decide to apply. Substation and feeder load profiles are another one. This again just kind of helps with some of the minimum load and kind of existing penetration of DER, so you can kind of know how likely you are to kind of run into issues. Connected and in-queue DER, kind of the same deal, right? If there's a bunch of projects in front of you, you should probably expect it to take longer, and you should probably expect to run into maybe some more constraints along the way. So all of these information are really relevant and helpful from the developer side in understanding whether a specific site is going to be viable. Next slide, please. Okay, so that's the first use case. We can also, I mentioned, use the hosting capacity information for interconnection screening to basically use some of the data from the process to help improve efficiency, reduce some conservative assumptions within the process, and improve some of the timelines for interconnection. Now, it seems intuitive, but this has not been that commonly used. It has some overlap in some of the underlying data, but hosting capacity changes basically every time a system gets added. So it's hard to keep it current sometimes. But there are factors like minimum load as an example. Using actual minimum load data can be really, really impactful in the screenings rather than kind of relying on ballpark level 15% minimum thresholds. You can get some substation reverse power information that's really relevant to the screenings that can really reduce the amount of conservative assumptions going on in there. Implementation challenges to kind of what's holding this back from wider adoption. You have to be able to effectively model queue generation in some of the power flow and hosting capacity, which can be very tricky and changes if, for example, projects pull out of the queue. It can kind of upset the modeling process quite a bit and make some pretty big changes. As I mentioned, it's kind of a system-wide analysis. It may not be as trustworthy as something that an engineer spent a bunch of time poring over. It can be difficult to account for like site-specific factors. Generally, like a hosting capacity, you're not considering volt-var curves for new generation, co-located storage, and some other factors that may impact actual performance. And in some cases, the screening criteria are built into like state admin codes, so it's hard to change them anyway, and it can become kind of cumbersome to inject some more technical stuff in there. So those are kind of some of the things that hold this back from wider adoption, but there are a lot of pretty easy kind of low-hanging fruit items to use some data within the process to speed it up and reduce some of the conservativeness. Next slide, please. And then finally, last but not least, as a distribution planning tool, and this builds on some of the modern grid project integrated planning materials that Lisa talked about earlier. The first step in doing planning is knowing where your constraints are. Calculating hosting capacity is finding those constraints for DER, and then you can kind of use that as a base to jump off of into what-if scenarios for DER integration, right? If you are expecting a lot of growth, you can start to see when some of those constraints are going to materialize under different scenarios based on different forecasts. This is really kind of the foundational piece that feeds into that decision-making and investment loop. All right, next slide, please. Okay, so I'm going to go back to the maps just because this is where a lot of the focus historically has been. There are some design, what I'm calling tensions and trade-offs in here that are kind of why do we see so much variety in terms of maps, right? Different utilities make different decisions, but some of them are really awesome and really useful, and some of them are really not. And how does the sausage get made, right? Where are all of these kind of tension points at? So the first one that I'll cover here is update frequency, right? How often is the data getting refreshed? In a lot of cases, it's annual. In some cases, it's even slower than that. More advanced practice is faster. Generally, monthly is pretty good. In some cases, bi-monthly. I know moving from like quarterly to monthly, kind of increasing over time is pretty common, but there are some trade-offs. So the utility increasing the frequency can drive up some of the maintenance costs or some other things, but it makes the information more trusted and more useful from the developer perspective, right? So striking that balance based on what's available. Similar on the geographic granularity side, how small or how big the area covering a specific results block is. If you have aggregated maps, they can reduce the risk of like utility assets and security, physical security. On the flip side, having more detailed maps helps improve site selection, right? So there's a balance, that there's some factors to consider in the design there. The amount of information provided, just like what kind of information on constraints, on load, on calculations. More information is almost always better from the developer side because it gives you more to go on and more to make decisions, but it can increase the cost of development and some of the update costs kind of depending on what specifically is in there. Cybersecurity kind of ties in with the geographic granularity. Highly detailed information may have some CEII in there if you're not careful, or may potentially expose distribution to some additional risk. At least that's been the argument. On the developer side, these are outside of distribution substations, not part of the bulk power system, and a lot of the information is available from Google Street View, right? Where is the substation? Where are the lines at? Some of that type of thing. There's a lot to consider in there. Cost burden is a big one. The more that's going on, the higher the cost to develop in some cases or refresh, whether or not, excuse me. And then finally, data export and tabular format. As I said, the map is the most common, but there are some utilities that allow for data to be exported or put into tabular format. The tabular results can be really useful for doing like site prospecting. Instead of having to click an individual location every time that you want to check it, you can export them all and do some batch processing. So there's a lot of kind of design decisions to be made in here, and you can kind of see that play out in all the different maps that utilities put forward. Next slide, please. Use case examples. So this one, this is examples of use in the screening process. California, I believe, has this incorporated within Rule 21. There's a mandate within the ICA to use the results of the hosting capacity analysis. PEPCO in DC, which is where this screenshot on the right is provided from, has sort of a heat map approach for, this is based on a stochastic analysis of where is the sort of like limit where I start to see issues. Then you have that kind of yellow region where it kind of depends on the size and location. And then at the red side, it's like, all right, we can't add any more anywhere. And the feeder becomes effectively closed from their perspective. So it is used kind of in these examples for the screening process. Next slide, please. Also wanted to touch on HECO, which has this in for screening and a little bit on the planning side, which categorizes each of the feeders based on how it's meeting hosting capacity needs and whether or not modifications and upgrades are kind of required to meet the expected growth in DER in these individual feeders. So it does feed into the forecasting and decision-making is being used for planning purposes. Next slide, please. All right, so that covers us for hosting capacity. I want to dive in now to non-wires alternatives on the capacity side. Before I get into it, I'd like to hear a little bit about where everybody's at coming into non-wires alternatives. There's a lot of industry discussion and a lot of sort of divergence of opinions in some cases. So I want to know which of these best describes your initial gut reaction to the phrase non-wires alternatives or non-wires solutions, depending on where you're at. Is it kind of, what does it mean? Is it, oh, hey, that sounds like a good idea, opportunity and optimism, is like it's complicated or super frustrating? I'll put my own vote.
Coming up on 2/3 of people responded. Let's see if we get a couple more.
All of the above. That should have put that one on there. That would have been a good option.
All right, we've got about 3/4 of people responded. Cody, I can go ahead and end it and share results if you like.
Yeah, let's do it. Okay, so we've got a pretty good mix and nobody's frustrated, which is very encouraging. So a little bit on the definition side, a lot of optimism and some kind of recognition that there are some complications in there. So that's good. This is very encouraging. So let's dive into the weeds of what does a non-wires alternative mean and how do we kind of go about achieving them. Next slide, please. Okay, so non-wires alternative is sort of the using a non-traditional means of on the transmission or distribution side, generally NWA's distribution, to defer or replace what would otherwise have been building new equipment, new poles, new wires, new transformers, by instead using a DER-based solution. By kind of definition, an NWA has to be as effective or more cost-effective, kind of consistent with classical planning principles. There's really 3 categories that we talk about for NWAs in distribution. The first is capacity. This is reducing thermal loading on equipment and kind of enabling more load to be served across the same infrastructure. When we talk about reliability here, we're specifically talking about the ability to have an alternate source during a loss of utility supply. So it's able to act kind of on its own if you lose the grid source for a variety of customers, not just an individual. And then voltage support is in here as well. This one gets a little less attention just because voltage support equipment tends to be a little lower cost. So it doesn't have as much kind of on its own, but it is a really important support element that DER can provide. Next slide, please. Okay, so when we talk about NWAs, we kind of have different levels of what I'm calling targeting. So you have these system level initiatives that don't have like a specific locational driver where any kind of specific impact to an individual location is incidental. And I think like LED light conversions and like net metering are good examples of this, right? You have net metering, doesn't matter where you put your DER, it gets treated the same system-wide. The next level down is a little bit more targeted. So geo-targeted programs tailored the programs and the incentives to specific areas where there's expected to be future distribution needs. Value of DER tariff is a good example of this. In New York, the VDER tariff has the locational system value where certain pockets of territory have a higher value because of expected constraints. And then finally, all the way down, specific grid needs. This is a dedicated procurement of a specific size and type of resource to meet a specific constraint. So a microgrid in a location, or I need a 0.5 megawatt for 5 hours at location C on substation A. Very detailed, very specific, very kind of down at the actual execution level. Next slide, please. Okay, so NWAs, what comes up a lot is how do you evaluate cost effectiveness? Generally, we're looking at a variety of different factors and comparing kind of the cost of the non-wires alternative to the cost of the traditional means of solving the same problem, and also including some of the other benefit streams we may get from non-wires alternatives because they are energy resources, right? So this example is from Excel's IDP from 2023. You can see we're including energy regeneration benefits, right? It is an energy resource, it's doing energy things. Generation capacity value, transmission capacity value, the deferral benefit on the distribution, which is kind of the goal of the NWA, is actually a pretty small portion of the overall like benefits of the device. But it is sort of the reason we want to put it on the distribution system. Greenhouse gas emissions is on there as well, and then the actual costs themselves. So these are kind of common considerations in the NWA is what is the full set of benefits of this solution, and how does that compare to the full set of benefits and costs from the traditional? And that's how we kind of decide where these make sense. Next slide, please. Okay, so I talked about a little bit on alternatives, right? We're comparing NWAs against other means of doing the same thing. So we have to include this within the planning process. And it becomes a little bit more difficult because we have to kind of make sure we're doing things in parallel. So in order to execute an NWA, first I have to figure out what my traditional solution would be. I have to kind of figure out how much it's going to cost. And then generally you're looking for candidate projects for NWA based on a specific set of filters, right? So it could be size, it could be price is a common one. If in a lot of cases, if the traditional solution is more than, let's say, $2 million, utilities may be required by their regulator to do an NWA analysis of it and screen it for potential. In other cases, it may just be kind of looking out for specific criteria, but like some method of screening potential projects for NWA applicability. Once you get through the screening, you have this kind of solicitation procurement phase with a more detailed kind of screen of specific proposals, and then kind of proceeding through engineering and construction. So that's kind of the life cycle of an NWA project. Next slide, please. Okay, so on the procurement side, there's a couple of different ways of getting an NWA in place. Kind of, again, we're going to harken back to that geographic level of, is it specific need versus geo-targeting versus system level. And then on the procurement side, sort of a direct procurement versus services versus kind of a program. Direct procurement is I'm going to go out and buy a specific thing or contract with a specific vendor for X equipment of Y size at Z location. Whereas distribution grid services is more along the lines of, hey, this guy over here is operating a battery. We're going to have control and operation of that battery for 10 times a year for 10 years to meet our local need, right? It's distribution services. When it's not doing that, I don't really care what it's doing. It's more of sort of focused on the specific distribution need and leaving the rest of it up to the owner of the asset. And then at the sort of geo-targeting and system level, you may have programs as a way of providing customers with incentives or information or facilitating adoption, DER value, energy efficiency, those kinds of things as well. So those are our kind of procurement mechanisms. So we'll finish up by kind of walking through some examples on the next slide. So this is an example of a specific grid need from my backyard here in Illinois, down in Thebes in Southern Illinois. We had a location where the town of Thebes is about 300 customers, historically a worst performing circuit for several years because it's served by a radial supply that runs through the Mark Twain National Forest. Very difficult to trim trees, lots of challenges on the reliability side, and not really any good solutions in terms of building another tie, because it's like 12 miles to the closest next substation. So rather than pursuing that option, they opted to install a 1 megawatt battery and use it as an auto transfer voltage source during an outage. So when we lose the utility supply, the battery takes over and islands the town while the repairs get made. And there's already been some pretty significant reliability improvement there as a result of this battery. So that's one kind of reliability driven example case. Next slide, please. I'll also show, this is a Colorado example, again, a specific grid need, kind of taking the distribution services approach. So this is a feeder that has a capacity constraint that they're trying to defer upgrading. It's about a $4 million project. They're trying to defer it out 6 years by using DER. And this was put out for competitive bid in 2023 with all of the information shown here, right? So this is the specific amount that we need. This is the number of hours, the specific duration, and the kind of expected hours in which it has to operate, and put out for bid for, please figure out how to provide 4.6 megawatts during these hours for this time period. Let us know how much it's going to cost, and we'll kind of pick from the best bids. Unfortunately, there were no bids. Illustrates some of the challenges of non-wires alternatives in the contracting side. You can do all of your engineering homework and kind of build the best proposal, but the contracting piece is also important. So there's a whole report on kind of lessons learned and ways to improve that. But this kind of approach can work, and it's being tried and deployed both in Colorado, I believe California, and some others as well, and kind of improving on some of the procurement pieces to get this to work effectively. Next slide, please. Geo-targeting is another option, and this one's close to my heart as we're working on this here in Illinois. So geo-targeting, kind of taking a customer-centric approach. Instead of going out and trying to procure resources, it's kind of having a program to direct customers who are in areas that are beneficial to adopt by providing them with additional incentives. So I mentioned New York's VETR, the locational system relief value. There are specific pockets of territory where it's more valuable to have, for example, solar, because it helps offset demand and reduce the amount of investment, and those get additional value. In Illinois, we have a proceeding ongoing to determine and kind of compensate the value of DER at a locational level to help direct investment and customer resources to those areas. So this is a method of sourcing NWAs that is a little less specific and helps kind of engage customers in being part of the solution, which has some of its own challenges, but also quite a bit of promise. Next slide, please. Okay, and then finally, one more example, the Central Hudson Peak Perks program, where they kind of used direct management of customer air conditioning systems, either through an on-off device or through thermostat set points, to help defer upgrades in a couple of specific targeted zones for substation upgrades. This was kind of structured so that the utility benefits, as do customers, by kind of looking for cheaper options through demand response rather than building infrastructure, where customers received an enrollment bonus and then specific bonuses for participation in each event where this was called. Next slide, please. So through this program, they actually exceeded their goal across the 3 locations. I think they were looking for a 5.3 megawatt target. They ended up achieving about 5.9 megawatts of load reduction, targeted in these specific areas with T&D needs. Overall, the cheapest load to serve is the load that's not served. So energy efficient, their demand response, excuse me, in this case was able to be a very successful non-wires alternative that was cost effective for the customers. So those are just a few examples. On the next slide, that should cover us. So yeah, that's just kind of a high level look at hosting capacity in NWAs. Happy to answer any questions that came up in the chat that I haven't seen yet.
Yeah, thanks, Cody. I think we have a few minutes for questions before break at the bottom of the hour. So I don't see any unanswered questions here in the chat, but if anyone would like to come off of mute, raise their hands, or just put a question in the chat, we do have a few minutes. Okay. Well, Cody, thanks so much for that presentation. We can go ahead and take a break for 10 minutes. Why don't we come back? So right now it is, well, it's almost 3:30, but why don't we come back at 3:40 with Natalie will give a presentation at that time. So we'll see everybody at 3:40. Thanks again, Cody.
Thanks, everybody.
Hey, everyone, welcome back. We are back with Natalie Mims-Frick, Berkeley Lab, and she's going to talk about virtual power plants made up of distributed energy resources connected to the distribution system and how they can provide a host of grid services. Natalie?
Thanks, Lisa. Can you hear me okay?
Yes.
Thank you. Thanks, Miles. We can go on to the next slide. As Lisa said, I'm going to be talking about, oh, we're going to do a poll first. I forgot. And I think, Miles, you're administering the polls.
Yep, I'm launching it right now for you.
Awesome. Thank you. So the question's actually supposed to be virtual power plants, not non-wires alternatives. So just assume that that's what it says. So instead of NWA, it says VPP. Are solutions that are composed of existing efficiency programs, front-of-the-meter batteries, demand response programs, solar plus storage, or all of the above. And I don't know if we can go on to the next slide while we wait for people to answer the poll, or I guess, Miles, you can see how many people are answering and you can shut it down whenever you think we've received the appropriate amount of responses. But
Sure, Natalie, we're at about 55%. I'm happy to shut it down and share results if you like. You can see what people thought.
Sure. Yes, all of the above is the correct answer, which I think was probably intuitive. But thank you, everybody, for answering. So here's the answer on the slide. VPPs are aggregations of distributed energy resources, or DERs, such as smart appliances and solar plus storage, EVs and chargers, and commercial and industrial loads. And this is the definition from the Loan Programs Office at the Department of Energy. And this is also their graphics that they provided from their VPP liftoff report. A few other notes about virtual power plants. Generally speaking, they operate at the grid edge, meaning that they are below the substations in terms of where they're located on the grid. It could be front of the meter, community solar, or behind the meter, solar plus storage or demand response programs, but it's generally further downstream. And one difference between VPPs and non-wires alternatives that's a little bit confusing is that non-wires alternatives are pretty locational based, as Cody was talking about. And historically, virtual power plants have been focused on providing system-wide benefits. And so you're aggregating programs across, your entire utility service territory as opposed to just one specific location. That being said, a non-wires alternative can be part of a virtual power plant. So they definitely have a relationship together, but the virtual power plant is kind of the bigger circle with non-wires alternatives inside of it. We can go on to the next slide. So this discusses, again, from Loan Programs Office at US DOE, what some of the value propositions of VPPs are. So they have a lot of value to consumers and to the grid. And from a grid perspective, VPPs can provide resource adequacy by integrating distributed generation and storage capacity onto the grid at times of high prices and demand. They can be used to improve reliability and resilience by integrating backup power onto the grid. And there's also incentives for consumers, both to own their batteries and then operate them in a way that is going to be advantageous to them as well as to the grid. They can provide transmission and distribution system relief, like through non-wires alternatives. And then from a consumer perspective, VPPs can help keep the grid affordable by deferring investments in generation and avoiding fuel. And then it also, as I mentioned, is creating an additional value stream for consumers for the resources that they already own by allowing them to participate in providing grid services and also allowing consumers to optimize their consumption and have greater control of their energy use. And then, more broadly, the programs can also be designed to fit, to help meet state policy goals, such as decarbonization or affordability or equity, resilience and reliability as well. So we can go on to the next slide. Today, the state of VPPs are that all of the vast majority of VPPs that exist are demand response programs right now. And they, for the most part, produce or reduce peak demand. And their performance is a little bit limited, typically by lack of communications and visibility and control. So the graph on the top shows DR program enrolled capacity by customer segment. And residential is the teal line, and industrial is the dark blue line. And as you can see, residential and industrial capacity has been increasing over the past few years, while commercial demand response capacity that's enrolled has been decreasing. This is from EIA 861 data, the Energy Information Administration. And then this graph on the bottom shows the cost per kilowatt for the programs by customer segment. And so when we look at the chart at the top with the residential capacity increase and the chart at the bottom, costs are decreasing. So we're setting ourselves up to be able to scale these programs cost effectively and move from just aggregation of DERs and the lessons that we've learned with those to aggregations of diverse DERs and VPPs. Currently, most VPPs are owned and operated by utilities, and some typical programs are smart thermostat programs or bring your own device and bring your own battery type programs. And we can go on to the next slide, please. I'm going to talk for the rest of my slides about some opportunities to accelerate scaling VPPs. And this is work that is in progress for a report we will be releasing in the near future about opportunities to scale VPPs. And so I'll talk through each one of these 6 different points on the rest of my slides. So I won't focus on them right now, but the graph on the right side of this slide is from DOE, and they identified that virtual power plants could provide 10 to 20% of peak demand in 2030 if scaled. So we can go to the next slide, please. This is the first theme that I had listed on that last slide, and it's around developing clear goals and objectives. And similar to what I would imagine Lisa mentioned this morning about integrated distribution system planning and making sure you have clear goals and objectives, it's important for VPPs as well. In part because there's many, many, many different definitions of VPPs, and it can get very, very confusing to talk about them because it's not clear if you're talking about a demand response program that is providing emergency capacity and is called on 4 times a year, or if you're talking about daily or multiple times per day dispatch and control of much granular grid services. And so it can be challenging to talk about VPPs, particularly between different actors, whether it's the utility and an aggregator that they're trying to develop a program with, or between a utility and the regulator. And so to avoid misunderstanding between the different parties about what we're talking about, we identified that, clearly defining what your use case and benefits and goals are is an important thing when you're talking about VPPs. So a few of the aspects that are useful to think about when you're talking about VPPs are, what are your desired grid services? What DERs can participate in your VPP? Do you have standards or protocols for the DER resource participation? Are you trying to target a specific customer type, such as low to moderate income residential customers or perhaps large industrial customers? How often are you going to use your VPP? What policy goals are you going to try and achieve with your VPP, whether that's, reliability or affordability? And then how are you going to determine if your VPP is cost effective? And I think, similarly, and I'll touch on this a little bit more later, how will you determine when your VPP is a success, particularly if you have a pilot and you're looking to move it into a full program? We can go on to the next slide. The second theme is around organizational change. One of the things that we observed in our interviews, we talked to a lot of different folks to help inform this report, is that integrating DERs into grid operations and engaging all levels of the company, in particular a utility, is very important when creating a VPP because the roles and responsibilities span across multiple utility silos. And in particular, you're going to be talking to your customer service team or your DER resource team, customer solutions, people who are reaching out and touching customers, as well as your grid operators and your grid planners and your IT department and your regulatory affairs to create a really strong and robust strategy that can be implemented and moved forward. And all of these entities have to be on board with the VPP and helping to support it for it to really be successful because it needs to operate and the grid operators need to know that it is there and want to use it. It needs to be included in planning so you actually are saving money by having your VPP and either deferring or avoiding investments or reducing fuel costs. And your regulatory team needs to be communicating with your regulators about the cost of this VPP, the investments that need to be made, the benefits that it will provide. And this is a little bit of a shift away from conventional grid practices, and keeping everyone engaged and moving forward is one of the things that we saw that really resulted in a successful VPP and having a champion. We can go on to the next slide. The next theme that I'll talk about is designing your programs for your customers. And this is not a new concept. It's something we've talked about in the energy efficiency world for quite some time. And it's broadly applicable to, any program that you're trying to motivate customers to participate in. But specifically around VPPs, utilities and aggregators can focus on what the customers are interested in. And so the example that I have here around opportunities to create additional value streams for customers' resources is the SMUD My Energy Optimizer Partner Plus program. And this is a bring your own device program where customers can enroll and receive a new value stream for participating in SMUD's program. And it's a battery program and helping to meet grid needs. So the customer can use the battery for their own resilience or to mitigate their own energy charges, and then also receive that additional value stream from the utilities for participating in their programs. The second one is around identifying customer priorities. So understanding what your customers are actually interested in, whether that's resilience or affordability or some other priority that they have, and align your program incentives with those needs. And the example I have here is for Portland General Electric, and what they have with their flex load program is geographically specific incentive levels, and they are providing higher incentive levels to historically underserved communities. And they're targeting these programs in areas where customers have identified that they don't feel that their reliability and resilience is high. And so that's one way that VPPs can be designed to try and meet customer needs. And then this last one is designing cost-effective programs for low to moderate income customers and help keep the grid affordable for all customers. And the example I have here is from National Grid, and it's actually all of the utilities in Massachusetts that are participating in this program with Generac, and it is a GRIP grant that was awarded in 2023. And Generac and the utilities are able to leverage federal funding to install up to 2,000 free batteries, which is effectively doubling the size of their low to moderate income program and really making it more accessible to more customers. And so that's a nice example of trying to find ways to leverage federal funding, but also to serve your customers that are in the most need and also provide grid services that benefit all customers. You can go on to the next slide. So for this next theme is on identifying, making sure that your grid planners and your operators believe that VPPs are credible and reliable resources. And this is a challenge that demand response programs have also faced historically. And there's a couple of different strategies that we observed that utilities can do for this. The first one is around conducting pilots. Not every VPP needs to be a pilot. In particular, if it's a well-known demand response program and you're just aggregating resources, then perhaps you can skip over this step. But pilots can be useful to help grid operators know that the resource is going to show up and that they can dispatch it, or that customers will participate in a way that is meaningful enough to produce the grid services that they need. The second one is on utility ownership of assets. So the utility can own and operate assets that are in customers' homes. This is a little bit of a can be a contentious idea, but the example that I have for this one is from a cooperative utility where they installed and owned batteries for customers and operated them, and customers could use them whenever the utility was not needing them to mitigate total electricity cost for all co-op customers by reducing their system peak. And the rest of the time, the customers could do whatever they would like with them. The third example I have here is setting technical standards for participation. This was an example that we saw from Rocky Mountain Power, where they articulated what the performance criteria for batteries needed to be in order to participate in the program. And so this opened up the program to additional vendors and aggregators, and also put the ball in the manufacturer's court to determine if they wanted to make modifications to their design to be able to participate in this program, and made it a little bit more transparent. And the grid operators knew that they were going to get what they needed because the resources that were showing up were meeting the standards that they had set. And then this last one is involving distribution system operators from planning to implementation. And this is aligned with the idea that I mentioned earlier of organizational change, and making sure your grid operators are part of the planning, that they understand how the program could be operated, that they can contribute to the discussion about what the program needs are and what the parameters for performance are. We can go to the next slide. So this is about how one of the themes is that you can aggregate your existing DERs to quickly scale a VPP. And one of the examples that we have from this is from Arizona Public Service, where they went from 48 megawatts to 145 megawatts of enrolled capacity for their smart thermostat program in 2023. And so it's a pretty significant increase. Quickly developing resources that can be dispatched in a short period of time is something that a lot of people are interested in right now, especially as we're facing load growth for the first time in a long time. There's another program that we came across that was able to scale really quickly, which was in Puerto Rico, and they have a virtual power plant that's batteries. And I believe they went from 0 to 7,000 customers enrolled in 1 year. And they have about 10% of their system peak capacity enrolled in batteries right now. And so that's also another good example of very fast scaling. The map on the left side of the slide is some forthcoming research that we have where we went through EIA 861 data and identified demand response programs and solar plus storage installations that have not been aggregated into VPPs, and identified the potential for existing DR programs to be aggregated together, as well as the solar plus storage. And we're still finalizing those numbers, but it's around 50 gigawatts of demand response potential.
Hey,
We
now
can go
we
on.
have
Yeah.
1 minute. Why don't we go to slide 13, the
Yeah.
action slide, and then we've got a question.
I was very long-winded. I apologize. Okay, so questions. For the co-op battery example, can you also talk about strategies for resolving customer concerns around utility oversight and device control? In our experience, marketing and outreach can be challenging as customers oppose control of their devices. We have seen this in some EV charging controls and quite a bit with smart thermostat programs. So for strategies for resolving customer concerns, I don't have a great example off the top of my head. One of my colleagues is doing research on how to develop robust participation in VPPs. And so I'm sure we can share that report with you all when it becomes available, and it talks about different ways to design programs so that customers are interested in continuing to participate.
Natalie, I think one idea that's certainly being used is to limit the number of times that the utility exercises control.
Yeah, I think that's one aspect of it. I think that having the opportunity to opt out is probably the biggest thing that customers are most interested in being able to do. For the Puerto Rico example, it's pretty unique in that they didn't require the customers to um, determine how much minimum capacity would be left in the battery on a contractual basis. So the customers could decide how much they wanted to provide to the grid every time an event was called, which is pretty unusual and gives the customer a lot of flexibility. Some of the other examples that we've heard from the customers were not as concerned about oversight and control when given the option between a higher incentive payment if the utility is allowed to control your asset, or a lesser incentive payment if you control it. We have been seeing people choosing to have the utility control it and receive a greater incentive. So I believe that over time, these are a couple examples of actions that states can take. I will be around and can answer chats if any of you all have any additional questions. And thanks for the opportunity to share some of this research.
Great, thanks, Natalie. Next up, we have Samir Sukkar from ICF, who's going to talk about identifying grid needs and evaluating investment options. So this is where the rubber really hits the road. You've got to, you're doing your distribution planning, and what do you need and what are you going to do about it? Samir?
Perfect. Thanks so much, Lisa. Yeah, so I'm gonna build on the conversations we've had already. Gonna really be talking about two things. One is investment prioritization, and the second is cost effectiveness. So moving to the next slide, we're gonna start with kind of that taxonomy from objectives to functionality that Lisa described earlier as a way to sort of underscore the relationships there, look at an example, but also look at it in the context of kind of utility budgets and think sort of putting some context around some of those investments, and then looking at sort of working our way back up that taxonomy in the context of prioritization. But then as we look at that, there's the possibility for some joint interconnected benefits that might inform the choice of cost effectiveness that we choose in various contexts. And then I want to end with a couple of questions that folks can pose on this topic. So jumping right in, you're going to see a familiar figure here from Lisa's talk. And essentially just underscoring what she mentioned earlier in terms of we're starting from principles and objectives, those high level sort of policy objectives we want to get to, and then working down toward the functionality and the individual technologies that enable those objectives. But to kind of illustrate that, I want to show an example. So moving on to the next slide, in the context of reliability, we can think about an objective like improving the customer unplanned outage duration, right? So here we're looking at an objective like getting to a second quartile in customer average interruption duration index. And we have sort of a timeline to achieve that objective. So the capability that supports that objective might be improving outage identification on the one hand and customer service restoration on the other hand. But then we can kind of decompose that in terms of some discrete functions, right? Where is the fault? What is the fault? Where is the fault? How do we isolate it to a specific part of the system? And then how do we restore the rest of the system and eventually the whole system, right? So those are kind of the four functions. And then there's a number of different technologies and investments that are going to then enable those functions, allow us to enable those capabilities and ultimately reach those objectives. So that gives you a sense of kind of how we move from objective to technology. But importantly, later we're going to be talking about those joint and interconnected benefits. You can imagine that a number of these technologies, some of these are field measurement devices, some of these are, software in the utility technology stack. They might actually enable more than one objective. That's what, we're going to get into kind of the relationships there as we go along. But with that as a backdrop, I want to take a moment and just kind of talk about how we think about categories of investments. So on the next slide, usually we look at grid modernization investments and kind of a big bucket. But it's helpful to sort of decompose that into a couple of different categories. And I've given a couple of examples here. For example, infrastructure replacement and upgrades. If you're doing a voltage distribution voltage upgrade from 4 kV to 12 kV, for example, line extension. This is kind of quote unquote new business, following issuance of a load letter or with a service upgrade. Distribution capacity expansion. So this relates to some of the non-wires examples that Cody was talking about. Hardening for resilience, for example, undergrounding. And then we get into grid technology. So this is kind of the grid management and monitoring, both the hardware and the software, IT, OT kind of investments. And then administrative, right? So meters, backend software, billing software. But I wanted to start the next poll and focus on that second to last bullet there. So for the grid technology, right, the grid modernization, the grid management, the monitoring, the IT, the software, what fraction of the overall utility budget do you think that constitutes? So going to the next slide, which I think is our poll, with a couple different options here between 0 and 60%. So if we could flash up here the options. So again, so looking at the entire utility budget, both CapEx and operations and maintenance, what percentage of that do you think is grid technology? Kind of the grid modernization, grid IT kind of components. Give folks a chance to think about it. And feel free to flash up the results when we.
Okay, yeah, we're at about almost 3/4 participation. I'll flash it for you.
All right, great, yeah. So it can vary from utility to utility, but typical number that we see is about 3 to 10%. So if we go to the next slide here, you'll see two pie charts. One is for the capital side and the other side for the operations and maintenance. And these are kind of nominally similarly sized components of the overall utility budget. On the left, you can see kind of the grid technology, 5%, information technology, 3%. On the right-hand side, you can see grid tech and modernization, 4%. So on the order of 3 to 10%, but can be more. It just depends on specific utility-specific circumstance, and it can vary from year to year as well, of course. So with that as kind of a backdropping, and it gives us kind of a sense of, the different components within the utility budget, and sort of decomposing it a little even more than those initial categories. The question is kind of, how do we get to a plan? How do we get to a prioritization across different investment types? And that's where we want to come back to those objectives. So going to the next slide, what we want to do, you'll see in the chevrons kind of a flow from determining the grid need to identifying solutions, looking at the cost effectiveness of those solutions, and then getting to that multi-year plan. Ideally, what we want is a plan that embodies, to the extent possible, the realization of the objectives that we set out, right? So that's, again, we're going, we've identified those objectives, and we want to sort of be able to score some of those planned investments according to those objectives and be able to sort of make those linkages. So how do we do that? First, we determine the grid need, and the first step might be to just kind of understand what the baseline is. So on the next slide, you're going to see a slightly different version of the utility technology stacks that Lisa showed earlier. This one, again, on the bottom are the kind of core platform components of the technology stack. On the top are those applications. And critically, the core platform components enable those applications. And that's, what we mean by joint and interdependent benefits, is that you might have something like ADMS that's on the bottom, the Advanced Distribution Management System, that might enable more than one application. And similarly, you might have, a given technology that's going to facilitate, more than one objective. So you're going to have kind of a one-to-many and many-to-one kind of relationship across these. And so what we're doing here with these gradients is kind of looking at the current status of implementation across the different components. And this is from Excel's grid modernization plan from 2023. And you can see different components are implemented to a different degree. And this gives you a sense of sort of what the current status is. And you can look at where there might be some needs with respect to fully deploying the functionality across some of these different components. So with that as sort of a baseline and identifying maybe some of the grid needs associated with modernization in this case, what we want to start to look at is not just kind of a discrete scenario, but looking at a couple of different scenarios to understand kind of where those investment needs might overlap across various scenarios, right? So this lines up with what we heard on the forecasting side in terms of taking a more probabilistic view. So going to the next slide, we see an example from Detroit Edison where they're looking at a high DG scenario or a high catastrophic storm threat scenario or high electrification scenario, and looking at where those investments overlap a couple of these different scenarios. And what that lets you do is start to look at what are those least regrets investments. And once you have those, then you can start to score those across your objectives. And so going to the next slide, we see kind of a conceptual prioritization across the various objectives, which are the columns here. And what you see are specific projects in the rows. And each of those are going to be scored across these different objectives. So this is a way, again, of we started from the objectives, we moved down to investments. Now we have a series of projects, and we're going to roll back up to objectives as a way to get to that prioritization. So again, this is kind of that investment prioritization. And one thing that we want to look at is kind of technology readiness level. So if we look at the maturity of some of these technologies on the next slide, what you'll see is you might want to mitigate the risk of either kind of technology obsolescence if you're kind of on the right-hand side of that S-curve, or technologies that are maybe a little bit too nascent, not ready for full-scale deployment on the left side. And as part of that, as an overlay of kind of that scoring, then that gives you kind of a sense of where you want to go and how you want to start to plan for and sequence some of these investments over time. So going to the next slide, this is an example of the Xcel Energy grid modernization roadmap. I think we saw this one a little bit before as well. And what it shows is, number one, there are a number of different elements here. Number two, as we described before, there might be deployment of certain core platform components that enable applications later on. So taking that long-term view lets us connect the dots between maybe those core platform investments and the applications that sit on top of those investments later on. And also it gives us kind of a long-term sense of kind of value and enablement by drawing those connections. So this is a really important sort of piece in terms of both sort of the breadth, but also the time horizon shown here that really allows us to kind of provide a kind of a basis for cost effectiveness. And I want to draw out one example. I think if you click through, you'll see a circle show up, which is FLISR. So FLISR stands for Fault Location Identification Service Restoration, which, if that sounds familiar, click one more, is this same slide that we saw a little bit ago, just a few minutes ago. So click one more time. So there's Fault Location Isolation Service Restoration. So that's what FLISR stands for. And what I wanted to do was just take a moment and provide a quick example of what this looks like in practice. So we took another example from Xcel, from their grid modernization, from a couple of different filings, looking at how they deploy this particular technology in the context of their overall grid modernization framework, which is what you just saw on the last slide. And so going on the next slide, here's a couple of data points pulled from Excel's Flizzr plan. And the important thing here is, number one, it's targeted, and number two, it's phased. So by targeting, by looking at the places, those feeders where they're going to experience the greatest value, they can start on the places where they know it's going to deliver the most value to customers in the near term and really kind of prove out the value proposition for this technology, number one. Number two, and that's kind of, in a way, it's kind of targeted and phased in terms of the rollout. So you're not doing it all at once. But number two, it's also phased in terms of functionality. So kind of starting on a local mode and then moving to fault location prediction, moving to open loop, and eventually to fully automated closed loop operation. So there's a couple of different ways to kind of look at this. And importantly, understanding the benefits. There's some important nuances here in terms of how you think about the specific impacts of Flizzr. I'm not going to get into the details here, but just to underscore the fact that understanding what those benefits are, and what the impacts are, knowing how to measure them is incredibly important. So moving to the next slide, then we get into cost effectiveness. And what you'll see here is we're going to be talking about lowest reasonable cost and benefit cost analysis. So if you look at the figure here, it shows how we move from, again, our planning objectives and priorities and utility circumstances through a set of expenditure drivers, and on the right, cost effectiveness methodologies, lowest reasonable cost and benefit cost analysis. So here I really want to focus on those on the right-hand side of that figure. But I will highlight the fact that there's a forthcoming publication that's listed at the bottom, economic evaluation of distribution grid modernization expenditures, a guide for utility regulators. Be on the lookout for that. I think it'll have a lot of interesting examples in there around how this plays out for different examples, different technologies. But what I want to highlight here is, the fact that you're going to look at essentially two different types of cost effectiveness. And they're both quantitatively focused, but they answer different questions. So I want to highlight what are the questions that they answer. So lowest reasonable cost, the way you can think about it is you've determined that a certain functionality is in the public interest, is in the interest of the utility customer. And so the question is, what is the lowest reasonable cost for achieving that functionality, right? And that could be safety and reliability or some other statutory regulatory requirement. But we've essentially established a functionality that's deemed to be in the public interest, right? So again, this is quantitatively focused method. It's based on engineering, technology, architectural analysis, and they determine the necessity and cost of a solution, a sort of a defined solution based on compliance with the statutory requirements. So that's why when you look at the expenditure drivers leading into lowest reasonable cost, it's largely standards compliance, but also regulatory orders and policy mandates, particularly when the regulatory orders include the finding that the required capabilities in the interest of the public and the utility customers, or if the policy mandate that identifies the value to utility customers, then you use lowest reasonable cost. If not, then you would use this other one, benefit cost analysis. Now, most folks know what benefit cost analysis is. In this context, the question we're answering is, will a specified or interrelated group of grid expenditures enhance welfare, right? Are benefits greater than costs for all or a subset of customers, right? So here, where we don't have that determination that either the regulatory order is in the public interest, or if the policy mandate doesn't specify that value, you might quantify those benefits and costs in the context of a benefit cost analysis here, right? So here, ideally, you have sort of a direct relationship between the investment and the value being enabled. Now, what I've been mentioning these joint and interconnected benefits a lot. That can be a reason to use lowest reasonable cost, right? If you're looking at ADMS, and a lot of the benefit is tied to applications that it enables, what you might decide is ADMS is in the public interest. You establish kind of that functionality and use a lowest reasonable cost as sort of a cost effectiveness method with respect to that advanced distribution management system, which is part of that sort of core platform layer in the utility technology stack. So this gives you sort of a flavor of what the two are: lowest reasonable cost versus benefit cost analysis, and some examples of kind of which ones apply in which cases. There are other capabilities that might lend themselves to benefit cost analysis. You'll see an example that's called out in the forthcoming report is around control center consolidation that might enable greater efficiency across the system. And so quantifying those benefits might be done in the context of a BCA. So that gives you a flavor for it. And then moving on to the next slide. The key here is that evaluation of individual grid modernization projects is insufficient to determine whether an overall distribution plan is reasonable, right? So we need to look at those relationships. It's important to understand the extent to which one investment enables value that's delivered by a different component of the system. So it's also necessary to understand, number one, kind of the extent to which the portfolio addresses one or more than one identified statutory regulatory objective, if it represents an integrated set of projects that are complementary, right? So again, kind of that joint nature represents a set of projects that are part of a series of expenditures. And then that's where we get into sort of the long-term plan and the importance of the long time horizon. Represents a prioritized set of expenditures given the urgency of grid needs that address identified statutory regulatory objectives and utility financial resource constraints. So again, that prioritization comes back to how do we get from objectives to investments, but then from investments back up to objectives, right? And then represents an optimized set of expenditures respecting customer affordability and equity considerations. So again, this is sort of looking at all of those objectives, which might include affordability, which might include equity and the like. And ideally, what you want to get to is kind of this value spend efficiency in the context of multi-objective decision making. So with that, I want to move to the last slide, which is it gives you a flavor for some of the kinds of questions that you can ask in this context. Have the clear objectives been established? What are the right planning objectives and criteria for your state's distribution system? Right, that could vary a little bit from case to case. What is the utilities grid modernization strategy and roadmap, and how will they meet those state objectives? So again, it's sort of connecting back between the capabilities, functionality, and the objectives, right? Thinking about that scoring that gives you that prioritization, and then the oversight and transparency is really important. Because it's, as you start to look at, some of these models, and some of which we've talked about today, the complexity of undertaking, these really detailed models can really require a lot of transparency so that interveners understand where the assumptions can meaningfully engage in some of these processes and understand some of the assumptions that underpin the outputs. So that's a really key one. And how does the plan address uncertainty in the pace and scope of change, right? So we talked about that technology readiness level There might be other pieces there in terms of sort of risk mitigation and the like, and how to use scenario planning and more probabilistic methods as well. So that gives you a sense of some of the questions. With that, happy to take any questions. As Lisa mentioned, feel free to raise your hand, call out, and really appreciate the opportunity. Thanks so much.
Thanks, Samir. That was great. Covered a lot of material very succinctly. Does anybody have a question? Samir is a real expert here. If you have a gnarly issue that your commission is trying to figure out, feel free to raise your hand now, put a question in the chat box. We have on deck Sean Murphy from Berkeley Lab, who's going to talk a brand new research that we have not published yet on data, metrics, and analysis in distribution planning, and specifically things that states can ask for. The utilities have it, should have it. One last chance. Any gone to ask Samir a question? All right, take it away, Sean. Thank you. Thanks, Samir.
All right, well, thanks, Lisa, and hello, everyone. My name's Sean Murphy. I'm an energy policy researcher in the Energy Markets and Policy Department at Berkeley Lab, alongside Lisa and Miles, and I'm glad to be here today to talk to you about some work that we've been doing on the data, metrics, analyses that you can request in integrated distribution system planning. Next slide, please. I'll start with some background and motivations and goals for this presentation. As Lisa mentioned, it is building from some ongoing research we're doing. So this is our sort of first public or somewhat public showing of some of what we've come to find, and we're looking forward to showing you more details in the future. But I'm going to be covering a number of different distribution system planning categories. I think you've heard some of those today. I just heard Samir talking about benefit cost analysis that will pop up here shortly, but we're going to be focusing on sort of the data, metrics, and analyses that you can request, sort of the data that can come out of IDSP and how that can affect your sort of planning and decision making. I'm going to try and cover most of these categories here. There are a few that I have in additional content in case we run out of time, but all the information will be there for your review later. Next slide, please. So before we dive in, I do have a poll question for you, which is, have you ever had more data than you know what to do with? But I get to answer my own poll here. All right, well, give everyone a second to respond.
Is this associated with personality type, Sean?
We'll see. I love data, but I have to admit, there are times when I've had more than I know what to do with. Will the poll pop up once it's done? Okay, here we are. 3/4 of you have had more data than you know what to do with. I'm definitely in there, and I'm impressed by, it's possible that some of you have not had to deal with large amounts of data, or some of you just aren't phased. Either way, I was sort of anticipating that folks have experienced this, and this is a challenge that can come up with distribution system planning. Utilities have tons and tons of data, and can you move to the next slide? There's tons of data that is in distribution system planning. Utilities have extensive data sets and they're diverse, and it can be a challenge to know first what's available, how the utilities are using that data, and what data you actually need to make informed decisions from your position, whether you're in a regulatory agency or say in a state energy office. These data are more than just curiosities and things to analyze they can really inform the decisions that you make. Lisa and I actually published a paper last year on how state energy offices can shape IDSP outcomes using, so I probably have a link in the slides there for anyone, just to give examples of how, even if you're not in a regulatory agency, you can sort of inform distribution system plans. But really, the data can give you the tools to ask the right questions, do analyses, and affect regulatory outcomes. The goal here is that after this presentation, you have a better understanding of what type of data is out there and what you can ask for and how it can impact decision-making. So for each of those different planning topics, I'm going to go through sort of high-level categories of the data and provide a few examples. There's more data than we could actually cover in 3 hours or 3 days. So we're just going to hit some of the high level, most important things. We will be publishing a paper likely in 2020, early 2025 about this that will include a spreadsheet that breaks down the important categories of data that hopefully you all find useful. And next slide, please. Okay, so we're going to start with asset management, which is when utilities establish an inventory of distribution system assets and analyze their condition and performance. Some of the key categories of data in asset management include the design standards, which provide transparency into engineering methods and design decisions, programmatic investments, which support assessments of the reasonableness and cost effectiveness of asset-related investments, asset characteristics, which describe the reliability, performance of assets, as well as configuration of the equipment itself. And finally, there's asset health and reliability investments, which explain how utilities can use asset health information to identify and then prioritize replacements of their equipment. Next slide. So for design standards, I'm just going to provide a few examples to give you a little detail on what's underneath the hood here. So design standards can include both construction standards, such as requirements for the availability of devices like voltage regulators. They can also include engineering standards that could include guidelines for undergrounding lines or replacing cables. These are sort of the rules that the engineers follow to make their decisions. They can also include assessments of different strategic initiatives. So this could be the cost and reliability impacts of a program that's focused on storm hardening. Next slide, please. So in worst performing circuit analysis, utilities analyze the duration, frequency, and number of service interruptions that customers face in order to identify the circuits with the worst reliability. Utilities often have reports on these circuits, and in those they can identify or provide data on the metrics and criteria for identifying the worst performing circuits. The metrics and these criteria can affect which circuits end up being worst. They also provide transparency for regulators so they can understand how the ranking is being done and which circuits are being selected. The data can also describe different characteristics of the circuits. This provides really important context for how the utilities can address reliability issues through remediation efforts. And finally, utilities can provide data on these remediation plans themselves, which show how utilities can respond to known reliability issues. Next slide. So now I'm just going to give some examples of different circuit characteristics that utilities can share. They can be pretty diverse, but they can include things like technical details, such as the voltage and line length of different circuits, the number of customers on a line. They can even be very specific, such as the number of customers on a medical rate, such as the people who need a higher level of reliability because they have some medical equipment that requires constant electricity service. And the other characteristics include reliability metrics, like the system average interruption frequency index, or SAFE, also the history of events, which could include the dates and causes, and then records on the maintenance as well. All of these data paint a picture for the issues that are affecting a circuit and then inform how you address those reliability issues. So in the table that I have here, it's from a recent report from New York State Electric and Gas. It provides sort of a summary of some of this information for an individual circuit. And tables like this help regulators know what the major issues are. So if you look in the top left, you can see that I think trees are the most common source of interruptions, accounting for almost half of the interruptions, but it's non-utility accidents that are causing largest sort of interruptions. So providing this type of breakdown helps regulators understand what are the causes and what are the drivers of the interruptions, which then can inform how the utilities should respond and address the reliability issues. Next slide, please. So in scenario analysis, utilities consider the implications of future grid conditions on distribution system planning activities. they manage uncertainty and they set bounds on what could and couldn't happen on the distribution system. They can't represent everything in the future that could happen to the grid, so but they are sort of plausible and set a realistic set of conditions. Other scenarios, utilities can report data including how they structure their scenarios. So this describes the areas of uncertainty and helps regulators understand how to compare different scenarios. Utilities can also identify the assumptions that really characterize their scenarios. So this helps you understand whether scenarios are aligning with particular policies, expected market and technology change, and climate change. Utilities can also describe some of the implications of their scenarios, which increases the awareness of risks and provides a starting point for discussions on mitigation and adaptation to those risks. Next slide. So there are a lot of different assumptions that can define scenarios, but a few common ones are the technology adoption levels, technology efficiency, and the operations of different technologies. So the table here is from Hawaiian Electric's 2023 Integrated Grid Plan. It identifies several parameters that define 10 different scenarios that it incorporates into its plan. One which I think is important is the use of managed first unmanaged charging, as well as fuel efficiency. So that reflects the sort of technology operations and technology efficiency sort of parameters that utilities can explore. Transparency on these assumptions is really important, just so it enables regulators to propose alternatives and really understand what's driving the outcomes that they observe or that are associated with different scenarios. Next slide, please. So next we have load and DER forecasting. Oftentimes those scenarios provide or frame the forecasts themselves. And utilities use the forecast to estimate peak demand at specific locations on the distribution system in order to inform the timing, the need, and the type of distribution system investments. Utilities can report a range of data on load forecasts, including the assumptions and modeling decisions that go into the forecast, as well as the estimates of peak demand themselves. As with the scenarios, transparency on the input assumptions helps regulators and stakeholders validate decisions utilities made and propose alternatives and understand how those assumptions align with what you're expecting to happen. And then the data on the peak demand estimates themselves give you a sense of what conditions the grid will face in the future. They help identify what drivers of peak demand growth are and can inform the strategies to then manage peak demand increases. Next slide, please. So as I mentioned, there's a lot of methodological decisions that utilities make in their forecasts. A couple of important ones include the types of DERs, distributed energy resources, that they consider, whether that's energy efficiency, rooftop solar, or electric vehicles. Being clear about what types of DERs are part of a forecast is really important because they can really affect load in the future. Additionally, the adoption rates of those technologies can have a very large impact. Utilities might explore low, medium, and high levels of adoption for heat pumps or light-duty electric vehicles. And depending on that level of adoption, you can have a very different outcome or for peak demand at both the system level and for individual feeders. Utilities can also address different levels of efficiency. So for heat pumps, that's often in the coefficients of performance. And as utilities can also make different assumptions about operating characteristics. So with EVs, that would mean managed or unmanaged charging. And for batteries, that could be the discharge profile. The figure that I have below here shows National Grid New York's projections of heat pump adoption across its system. It uses this sort of statewide adoption, which is aligned with some decarbonization pathways. And then they have a method for allocating that statewide adoption to individual feeders so that they have sort of feeder-specific estimates of heat pump adoption and then therefore estimates of their impact on peak demand in the future. And next slide, please. So in hosting capacity analysis, utilities determine the amount of DERs that they can interconnect without infrastructure upgrades or adversely impacting power quality or reliability under existing control and protection systems. The data on hosting capacity analysis can include a number of things, including details on the methods that utilities use. This can affect the hosting capacity estimates themselves and also how a utility is able to use those results. The data can also include information on the distribution system infrastructure itself, which can inform the siting and of DERs, and even without the additional hosting capacity data. The data also can include information on the load in DERs, which again can inform where DERs are sited. And then there's the hosting capacity outputs themselves, which affect where DERs can be sited, how large they can be, and also how they operate. And finally, utilities can provide information on mitigation analysis, which can increase the hosting capacity by systematically addressing constraints to hosting capacity. Next slide. So the outputs of hosting capacity can be for generation, such as rooftop PV, load, which would include electric vehicles and building electrification technologies, as well as storage. On the right here, I have a figure or a screen capture from Excel Colorado's generation hosting capacity map. Maps can fall into one of two sort of broad categories. Some just show general areas or heat maps, and some have sort of sub-feeder level data. So this is an example of sub-feeder level data. If you see there's like a small box or aquamarine box that is showing the hosting capacity within a particular node on a feeder, and then this pop-up is showing some of the detailed information, including some of the data on the distribution system infrastructure, the constraints that the node is facing, as well as the hosting capacity. So this is a pretty detailed level of hosting capacity data that a utility could publish on a map. The heat maps may just have these different shades and then a band that says 3 to 5 megawatts or something. But this is a pretty detailed example. And if anyone is interested, you can follow that link and sort of explore how detailed that map can get. Next slide, please. So in grid needs assessment, utilities assess the constraints for distribution system assets under the forecasted load and DER levels. Utilities can share a range of data on grid needs and assessments, including the scope of the assessment, to provide some context for how that fits into the rest of the distribution system planning strategy. They can also describe their analytical approach, which is important just for having some transparency in the utility's assumptions and methods, and also enables regulators to propose alternative approaches and validate what the utilities have done. Utilities can also report the characteristics of those grid needs, which could include the type, the timing, and the scale of that need. And then also can provide data on the solutions for those grid needs. And that can help prioritize which grid needs being addressed and the solutions being used to address them. Next slide, please. So I'm just going to give a few examples of the type of data on grid need characteristics that utilities can provide. They can first include data on the distribution system assets in question. It's good to know exactly which ones are being addressed. So that could just be the IDs, where they are on the distribution system. Utilities can also characterize the type of deficiency or grid needs. That could be a capacity shortfall, reactive power, or voltage issue. And they can also describe the timing of that deficiency. So that could be the summer, particular hours, and then the magnitude of the deficiency could be in terms of the sort of megawatts or the number of hours that a deficiency lasts. So all this information is really important for understanding how to respond to the grid need and what solutions can address it. Next slide, please. In investment strategy and implementation, utilities are establishing long-term strategic plans to achieve distribution system objectives using insights from other parts of the distribution system planning process. Two of the key categories of data here are the strategy itself, which sets the vision for investments, provides important context on market policy and technology factors that may affect the investments, as well as the implementation strategy, which describes how the utility plans to achieve that stated vision. And next slide. So some of the data on strategy implementation can include descriptions of progress to date. So that could just be the list of top technologies the utility has already upgraded. They can also include the planned investments, which would be the technology that they plan to install, as well as describing their functionalities. This table below from Rhode Island Energy provides an example of that, of identifying different technologies as well as their functionalities. Utilities can also provide information on the costs and the financing for their investments, as well as strategies to identify and mitigate risks in the investment strategy itself. Next slide. In non-wires alternatives, utilities can use DERs to provide grid services at specific locations on the distribution system to reduce, defer, or avoid the need for distribution system infrastructure investments. Some of the key categories of data on NWAs that utilities can report include sort of screening criteria, or screening process, which indicates how the utility, whether it can consider an NWA given grid needs, costs, and timelines. There's also cost effectiveness information, which can inform the decisions to actually pursue the NWA by delineating different benefits and costs. And then there's a procurement process, which establishes requirements for requests for proposals for companies that might come in and provide NWA solutions. And then there can be data describing the performance, which provides a framework for measuring the impacts of an NWA and summarizing those impacts. Next slide. So some of the data that you might find on screening NWAs can include a description of the type of grid need being addressed. So that could include thermal loading or capacity, as well as the timing of the grid need. It's important to know whether it's going to be happening in 6 months or 6 years, and it's also important to understand sort of the costs of the investments and how they might compare to traditional investments. So this table that I have below is from Central Hudson, and it's showing their suitability criteria for non-wires alternatives. I'll note that it shows both some of these clear top cost and timeline criteria, and the lower end are sort of implying a sort of a minimum cost and a minimum timeline, since it does take some effort internally and take some time in order to prepare those investments. So clarity on sort of those cost and time planning thresholds can be important for determining whether to pursue an NWA. And I think we're onto the additional content section now, but if there's a little bit more time, Lisa, I'm happy to go into those, or we can move to Q&A at this point.
I think we can maybe go to Q&A if folks have questions. I mean, this is all about being familiar with what data you can ask the utility for, either in a prescribed distribution planning or grid mod proceeding, or, if you're at a public utility commission, certainly as a staff member, you have the ability to request this information off cycle, at any time, really. So I'm curious if anyone has any questions. I know we've been together for quite a while now. Appreciate the folks who were able to stay till the very end. It's pretty late on the East Coast, which is anyone have a question they'd like to raise their hand or they'd like to put in the chat box? Okay, I think maybe we should just let folks take the additional time so they can get work done that they probably need to do as well. So a couple more things. One is, please sign up for transportation electrification training on December 19th. We've got Nancy Ryan and Andy Satchwell. It's going to be a great presentation. And also before that, December 11th and 12th in Charlotte, we have an in-person training with all new curriculum and a real focus on electrification and distributed energy resources. We also have the same curriculum is going to be offered 2 more times in Detroit in March, and in the West, location to be determined in the West. All right, thanks very much to our trainers who are still on, and we'll see you next month. Thank you.